welcome everybody here. I was told that we have an unusually high, almost 100% retention rate in this class. This is actually first time from the first week of this class till today. And you have heard the wonderful lectures by wonderful leaders in this industry. Today is no exception. Christoph was previously robotics engineer at NASA, the Jet Propulsion Laboratory. After that, Christoph started his own AI robotics company, served as founder, CEO, and then the board director of more than one robotics company. Christoph is now the senior member of the technical staff at Nvidia. Now, Nvidia Supplies is a world leader in AI hardware, AI chips. I think some of you already heard that Nvidia has just broke the market cap of $1 trillion. Is bigger than Facebook right now, as it should be. Mr. Huang, the founder, a Taiwanese American born in Taiwan, has suffered through many challenges throughout not only his personal life and also growing Nvidia. I think at one point, Nvidia was investigated by SEC, and the market cap dropped from 100 billion to 10 billion, like within the day, lost 90% of the market cap. And Mr. Huang fought through it, continued to actualize his vision. And we have today one of the global leader, hottest tech company in the world, $1 trillion market cap. So what this tells us is that you guys will be the mover and shakers in the AI robotics field in coming years. You will suffer through a lot of personal feedback, and you have to stick your long-term vision, 10-year, 20-year, okay, going through the ups and downs, because as you become leaders, you will go, the market force is so strong, it is going to go up and down, okay, many times. So you have to continue to actualize it. And Christoph started his own company and moved to this leading company, also show this aspect of resiliency. When you reach the top, you fight against directly. You are in the chaos of the market forces, right? So you have the best role model, the leader, and also talking about the most exciting topic today. Without further ado, Christoph.
Thanks very much, Albert. Yeah, I'm super excited to be here. Let me try to share my slides. And if only I knew how to do that. Share screen. Screen two. All right, please let me know if you can see my slides.
Yes, I see it.
All right, awesome. Thank you, Elvin. Yeah, thanks everybody. I'm super excited to be here, and I hope you guys enjoyed this talk. As Albert said, my name is Krzysztof Ledomyski. I am currently a senior software engineer at Nvidia working on autonomous vehicles. And I do need to say that all the opinions I express here today are my own. I'm not here representing Nvidia. By way of introduction, here are some of the robots that I've worked on through my career. As Albert mentioned, I started at NASA JPL. That's that top half of a humanoid robot trying to change a wheel there in that picture. And then after that, I worked on a couple of different kiosks you see there on the top right. Industrial controls, that's top left. I didn't actually start that company. The company was started a little over 20 years ago now by my dad. I took over as CEO for a period of about 5 years. And then also worked on this autonomous lawnmower at the bottom left. And now finally, as I said previously, working at Nvidia on self-driving cars. And you're probably thinking, wait a minute, Nvidia doesn't make cars. And you'd be right. Nvidia makes hardware and software that it then sells to other car companies, which helps those cars drive themselves. Okay, so, and maybe one other thing I'll say at the beginning is that rather than diving deep into technical nitty-gritty details, what I'd like to do here today is focus on the larger arc of computational hardware for robotics, so that you guys kind of understand the trajectory and the story and where it's been, where it's going, why it's important. And I hope you get that out of that. And as Albert mentioned, I will leave some time at the end for questions. So this is an American on the moon in 1968. And that is really, really awesome. And at the bottom right, you see the guidance and navigation computer that got that guy and some other people there as well. And this computer ran at about 2 megahertz, and depending on how you calculate it, it was about 120 million times slower and less performant than the phone that's in your pocket right now. And it got these people to the moon. And so potentially a fairly reasonable question that one might ask is, okay, well, if you can do this amazing thing with this slow computer, why should robots today need really high performance computers, right? What's the big deal? And so to think about that, you know, if the moon was rotated a little bit in this image, you might see planet Earth, right? Straight line, and you would see all the way to Earth, however many miles that is, many miles. There's nothing between the moon and Earth. But the environments that robots have to operate in are actually significantly more challenging than that. And so even though the tasks that they may be performing probably look much more trivial at a glance, actually the computational demands of modern robots are potentially significantly greater. And so here's an example. This is an image from Tesla. And so this is the environment that the Tesla has to navigate, right? And it's clearly very complex. Everything is moving, right? Everything is close to each other, just less than a meter between a car and maybe a cyclist, maybe trees, maybe another car driving in the other direction. You have very little time to make decisions, right? It does me no good if I detect that there's a person walking into the intersection when I'm just about to hit him, right? I need to know ahead of time so that I can still stop and avoid a collision. And so there's a lot going on here, and the environments are very tricky. And in particular, one huge demand here is perception, right? Sensing the world around you and making sense of it. And so that is a major task that this robot has to do. Tesla, interestingly, I think they like to say that they have the largest fleet of deployed robots in the world. And if you indeed consider their car a robot, that's probably true. And so they arguably have more data from robots than anybody else. So let's talk about that. This is a different car. This is a Waymo. I'm trying throughout this presentation to use images and data from a whole bunch of different companies. So you'll see me jump around like that. So this is a Waymo car, and since you guys live in San Francisco, you probably have seen these. But look how many sensors this thing has. It's over 50 sensors, and it's a combination of LiDARs, cameras, including both the visible spectrum as well as infrared cameras, ultrasonic sensors, and radar, right? All around it, you have sensors. And the car, like I said, the car has to make sense of this in very, very little time and act accordingly, right? So if you imagine how much data that's coming in, you need to process all that, and therefore you need really high performance compute. So Let me say that again. So I think this car has three big constraints that it computationally that it has to deal with. One is there's a huge amount of data. Two, the data needs to be crunched really fast. And three, it's doing the same calculation over and over, both in terms of time, right? The kind of data that you get from every camera, it's just a set of pixels, right? And a second later, it's also a set of pixels. And a second later, it's just a set of pixels. So that calculation over time is the same. And then also the calculation over space is the same, right? If I'm looking for a person in, say, the left half of a camera image, I'm probably going to run exactly the same algorithm in that left half of the image as in the right half of the image, right? So huge amount of data, same calculation over and over, both in terms of time and space, and the data needs to be crunched really fast. Three constraints. I'm going to ask you guys to think about this for a little bit. Can you think of another application, computing application, where you have similar requirements, right? Lots of data, same calculation over and over, and you need to crunch it really fast. Let's take 30 seconds, each of you think about it. And if you want, feel free to type it into the chat. This could be fun.
I know you guys ask very good questions, and this is a very live question to think about.
All right, so hopefully.
Maybe like computer graphics or like rendering.
Yeah, I think that's a great answer, Noah. In fact, that's exactly the answer that I came up with when I was thinking about it. And so here's an image of Fortnite. Of course, Fortnite wasn't the first game, but I hear that's what everybody's playing. And so that's exactly what I was thinking. You have a huge amount of data, right? There's tons of objects in this world. You have reflections going on. You have shadows. You are doing the same kind of calculation over and over, right? The way that you calculate the value of this pixel is the same as the value that you calculate, the way that you calculate the value of this pixel, and you need to crunch it really fast. If you do it slow, your game's going to lag and you're going to be very unhappy because some noob's going to frag you, right? So basically what happened was chips that were developed for computer games could also be repurposed for robotics applications. And that's exactly what happened. Before I go kind of a little bit into that story, let's spend a little bit of time about the differences between the GPU and the CPU. So the CPU is the central processing unit. It's the central processor in your computer. And it does all the calculations. It does most of the calculations in your computer. And it's great in many ways. It's super flexible. It's easy to program. The paradigm for programming CPUs is single instruction, single data. So you're doing one calculation at a time, and you're doing it on one piece of data. GPUs were introduced for games, so graphics processing units, to parallelize things in a same instruction multiple data model. So you have the same kind of math equation that calculates the value of every pixel, and you're doing it on multiple data. So you're doing it for all the pixels in parallel, right? Because if you were trying to render a frame and calculating the value of one pixel at a time, it would be very slow. And so you parallelize that. And so the images, hopefully on the right, you can see kind of illustrate that. And so back in 2007, Nvidia had the bright idea that, hey, these chips that we make for games are really great. And I think they could be used for things other than gaming too. And so they released it, and there were some applications initially, but none of them were super kind of world defining or industry defining until a couple of different things happened. Bear with me for a little bit. We're going to talk about ImageNet. So you'll see me jumping a little bit between hardware and software, and that's because obviously the evolution of hardware and software are tied together, right? If software evolves in a particular way where a certain type of programming is really, really great and useful, then the hardware engineers make hardware that makes that software run better. And if hardware evolves a new particular capability, well, maybe software engineers write software that takes advantage of that capability. And so you'll see me kind of weaving through between hardware and software back and forth. So ImageNet is a image analysis competition for AI. It has something like 14 million images, and the challenge is basically detect what's in the image. And you're probably thinking like, well, that's not that hard, right? My phone does it. I just pointed at something and it tells me what it is. And that kind of capability was developed exactly through papers and algorithms that competed on the ImageNet dataset. And if we look at the results on that data set by year, that's the graph on the right, you see this gigantic improvement that happened in 2012, right? The error rate looks like it went from, say, mid 25% to about 15%, right? That's a huge improvement, right? How did that happen? And the paper that did that is called AlexNet. And the authors basically noticed that if you take a neural network, so neural network is a type of machine learning AI algorithm that very, very loosely mimics how the human brain works. And they noticed that, hey, the bigger you make it, the better it works, right? So let's make a really, really, really big one. And the only way and the bigger the network, the longer it takes to train, and the more power you need to train, and the more data you need to train, and so on. And so the only way that they could make this network so much bigger than their competitors was by using CUDA, what we talked about earlier. So they trained this model on GPUs, made it way bigger than anybody else before them, and that's how they got these great results. And then everybody else, they published these results and their methods. And then everybody else saw it and was like, wow, that's a really great idea. We should do that too. And so everybody started doing it. And you can see that by 2013, everybody had results at least as good as AlexNet, and they've been driving down from there. And that paper really kickstarted the deep learning era of AI. And so here's a chart over time about the amount of computation that you need to train selected kind of representative machine learning models over time. And so this is a logarithmic chart. Every horizontal line indicates an increase of 100 times in computational power, right? And so you can see it's kind of logarithmic exponential growth at one rate until about 2012, when AlexNet came out and was super successful. And then everybody was like, okay, let's throw everything we have at this. And then it just picked up once again. And then we had another kind of similar event with what the authors here are calling the large scale era. This is like the GPT, general purpose transformers, the large language models. And so that's another increase in magnitude. And these models now, by the way, they're so huge that it literally costs like over $1 million in computational resources and energy just to train them, right? It's just mind-boggling, right? I remember like training models on my little laptop with a little Nvidia GPU. And you can of course still do that for smaller models. Okay. Did we? Okay, so here's another slide that's based on data from Tesla. This is from a talk that Andrej Karpathy, who at the time was director of AI at Tesla, gave. And he coined this phrase software 2.0, but basically what he means by that is neural nets, right? And or maybe even more loosely, software that is written by neural nets, as opposed to software 1.0, which is hand-coded by humans, by software engineers. And so to make that little bit more specific and maybe more clear what that is, he gives this example of parked cars. In the software 1.0 world, you, a software engineer, think really hard about how you might detect a parked car. And you might come up with rules that go something like, well, I think the car is parked if the bounding box hasn't moved more than 20 pixels over the last 3 seconds, and it's in a neighboring lane, and kind of it's on the side of the road, and the lights are off, yada, 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 right? You come up with these rules. And of course that the way that you validate it is you run this rule on a bunch of data, and then you say, okay, I see some examples where this didn't work, and you might try a couple of different iterations of this, and then at some point you say, well, I think this is as good as I can make it. And so in the diagram on the top, that's the little red dot that you have there. And because you iterate, I think actually there's some arrow that there's a little bit of movement, but not so much. And in the software 2.0 approach, you gather a whole bunch of data. You say, okay, these are the kind of contours of the problem. These are the kind of sets of solutions that I'm willing to accept. Please give me, the model that best detects parked cars on this gigantic data set that I have assembled for you. And the model does this very, very complex optimization and ultimately probably arrives at a better solution than you have, right? And this is borne out by a ton of data. And so the model can come up with much more complex solutions than you and I can, right? It's not possible really for a human to kind of comprehend how exactly, for example, the network that powers ChatGPT works, right? It's just so gigantic, it is beyond human comprehension. And similarly, if we talked about ImageNet earlier, if you were to look at a subset of ImageNet as a human and try to write detectors for the different kinds of objects, I don't think that you'd probably get any improvement after looking at, say, the first 10,000 images, right? It's impossible for a human to hold in their head and conceptualize, create rules out of like more than 10,000 images. Whereas neural networks can do that, right? If you go from 10,000 to 10 million, the performance of the neural network gets a lot better. Okay, so software 1.0 versus software 2.0. And this is what Andre at the time saw as the evolution of software over time. So Tesla started with mostly 1.0 code, hand-coded by software engineers. And then they collected a huge amount of data, trained a bunch of models, and put in a neural network. And then over time, the neural networks are taking more and more of the software stack. And Andre gave his talk in 2018. And actually now, just this year, Tesla said that now finally they are doing control using a neural network as well. And so if you were to update this chart for 2023, actually this blue part goes all the way up to steering and acceleration, right? So it's still, we're still headed in that direction. We're not done yet. Here's another, I think, really, really cool example of software 2.0 taking over more and more of the stack. And it's getting a little bit meta maybe. So this is, the problem here is design a chip that has a certain capability, and you want to make it as small as possible. The smaller you make it, the more components you can get onto a smaller footprint. Maybe your final device can get bigger, etc. So everything gets better if you can cram more of these things in. And on the right, you see the result of kind of the traditional approach that this EDA tool, which is the kind of tool that you would use to create this layout. So on the right is an example that this EDA tool creates. And then on the left is an example that is created by AI. And it's significantly smaller. So it's a significantly better result. And why I really like this example is that this is Nvidia AI that's running on Nvidia hardware, designing the next generation of Nvidia hardware, right? So in kind of the original science fiction days, people saw this scenario where the robots start building the new and better robots, and then those robots build the new and better robots, and you just kind of get significantly faster, right? And in some ways, we're kind of already there, right? Super, super exciting. So to kind of summarize the main takeaways so far from this talk, the neural networks are getting bigger and bigger, and they are taking over more and more of the software stack. And therefore, we need more, better computational hardware. These are some examples of that. And because the need is so great, a bunch of companies sees it. And actually, the needs are different depending on exactly what hardware you're looking at, right? So the needs of your phone in your pocket are very different than the needs of, say, the servers that are running ChatGPT, right? Completely different set of constraints. And so each of these applications have their own kinds of chips. And so here I show some representative examples of all of them. Automotive is a great example, right? If your car is going to drive itself, as we talked about earlier, it needs to make sense of the world. It needs to process a huge amount of data very, very fast. And so there's a few companies that are working on making very high performance hardware for that. Tesla is one good example. And actually, Tesla is interesting because they were very early to the game, right? They started talking about self-driving and working on self-driving way before the idea became mainstream. And what they concluded at the time actually was that there was no chip available on the market that met their needs. And so, given their background as a tech company, they decided to actually design their own chips, and they've been doing that. And I would say it's impossible for me to imagine a traditional car maker doing something like that. And indeed, to the best of my knowledge, all the other car makers are using chips from established kind of chip manufacturers. So good examples are Nvidia, of course, as I mentioned earlier, but also Qualcomm and Mobileye. Okay, so that's automotive. Your phones obviously have AI chips. We talked about that, right? They figure out what's in the image that they just captured. They understand what you say to them, and so on. And so every kind of modern, powerful phone has usually, I think, multiple AI chips in it. And maybe an interesting piece of history, actually, Nvidia was in that market segment as well. That's how the Tegra line of mobile processors started at Nvidia, actually. And they were successful with it. But eventually, they concluded that actually it was becoming kind of a commodity game, right? Where basically the chips were starting to look very similar to each other, and that the differentiating factor very often would just be price, right? And Nvidia doesn't want to compete on price. They want to be able to offer a little something extra. And so they decided to exit that market and pivot the Tegra line to something else. And actually, that's how the Edge Robotics line of products, which we're going to talk about in a little bit, grew out. And actually, you can also trace that line to the automotive line, right? Where Nvidia believes they have better value add than in competing in chips for mobile phones. For very low-cost devices, this is not necessarily something that you might think of as a robot, or actually you probably would think of him as a robot, but it probably wouldn't be the first thing that comes up, right? For very low power devices, Raspberry Pi is a great solution. These things take very, very little power. They're very, very cheap. I think you can get them for something like $30. So they're used in a lot of IoT, Internet of Things devices.
Yes, Christoph, indeed. Our system team has been using a Raspberry Pi, and they were shown a cloud IoT-based robotic control system.
Yeah, awesome. Yeah, I love Raspberry Pis too. That's great. Have you guys used Jetsons also?
Well, I have to speak as a program executive director. So we did purchase some Jetson. We will appreciate for our students. Nvidia can donate some Jetson orange. I'm just fulfilling my role, but yeah, that will be yeah. Jetson is important. Yes.
Yeah, awesome. So I have a little video actually about the Jetson line, so I'll skip over that now, and we'll talk about it in a little bit. Desktop computers obviously have specialized graphics processing unit. Still the largest consumer is games, but you also use it in computer-aided CAD applications, computer-aided design, Photoshop, video editing, that sort of stuff. AMD and Nvidia have the most of this market. And then in the cloud, powering ChatGPT and really anytime that you train any machine learning models, train or deploy any machine learning models in the cloud, you are using a chip like this. And this is a super popular market or super hot market right now because of the success of ChatGPT. And right now, my understanding is that Nvidia controls over 80% of it, and people are looking at it like, wow, there's a ton of money to be made here. And so a lot of competitors are coming for it. Google is designing their own chips, Amazon is designing their own chips, Microsoft is designing their own chips, AMD is designing their own chips. So this is going to be a very, very competitive market. Right now, Nvidia though definitely has an edge here, and in fact, Jetson, our CEO, likes to say that our chips are so good that our competitors could give theirs away for free, and they would still be more expensive than ours, because the way that you come up with the cost of a chip like this is that you calculate the value that it creates for you over time. And if the Nvidia chips per unit of power that they take in produces 20% more calculations, then over the lifetime of that chip, the cost of the chip itself becomes negligible. And so even if, as Jetson likes to say, that if our competitors gave their chips away for free, they still couldn't. They still are more expensive than Nvidia chips. We'll see how long that lasts. As I said, this is a super competitive field right now. So here's coming back to robotics. Here's a little video of different Jetson powered applications, and you'll see this video has a good amount of variety. There's a bunch of delivery robots, applications that track cars or parking lots, straightforward computer vision algorithms, etc.
While we watch this video, next 2 weeks we will have former IBM Watson AI, former Apple directors introducing AI, machine learning, autonomous, and generative AI.
Great, good timing. And you told me also, Albert, that you guys are going to learn about simulation next very soon. And so I have a little slide here about NVIDIA's Isaac Sim as well. So simulation, maybe just introducing it very briefly, since I think you guys haven't covered it yet. Simulation is super valuable because it allows you to iterate much faster, learn safely, get to scale much faster, and discover edge cases, and so on. You can start actually writing software in simulation before you actually have the robot assembled, right? So simulation is super valuable, and just like in these many other fields related to robotics, a lot of companies are seeing that value, and they're now starting to make products to be helpful there. I think you guys are going to learn about Gazebo, which is kind of the granddaddy. It's nicely tied in with ROS, the robot operating system, but also there's other companies now that are entering this market. Nvidia is one, Unity also. if you think about it, it kind of makes sense if you approach this from a gaming perspective, right? Because in a game engine, you have to simulate accurate physics, right? In order for the game to be fun, you want to make the graphics really good, and kind of that already between those two things gets you really close to a simulator. Unreal is also making one, Microsoft, Amazon, and so on. So this is a quick video of Nvidia's simulation platform, Isaacson. And what's super cool about this is, to me, with some of these shots, I wasn't sure whether they were coming from simulation actually, or if it was a real video. And I think that's a huge advantage that Nvidia has, you know, taking advantage of that, of the background they have in computer graphics to make simulation that looks photorealistic. I love this robot Animal from ETH Zurich. This is one of the coolest robots I've ever seen. Okay, so that's Isaac Sim. And so as I said, one of the things that I think is a unique value proposition from NVIDIA is that the simulation is photorealistic. And in games, photorealism is cool because it, you know, makes the game experience more maybe immersive, allows you to more easily suspend your disbelief. But in simulation, it actually has another really crucial value add, which is that it allows you to use the same computer vision models in simulation and in the real world, right? So if you have a neural network and you train it in a bad simulation and then you try to deploy it in the real world, it's just going to fail horribly, right? Whereas if you have a really good simulation that's photorealistic, hopefully you can use the same network both in the simulation and in the real world, and that lets you accomplish things much faster. And indeed, this is what companies are doing with Isaacson. And then I think one other thing that is unique to NVIDIA's simulator is that it's tied with NVIDIA Omniverse, which is just a huge collection of 3D models that you can then bring into your simulation. So you can create these very rich environments, which allows you to create a wide variety of synthetic data that helps you train those models and evaluate a wide variety of cases in your simulation. Okay, stepping back now a little bit from some of these details. The future is already here. It's just not evenly distributed yet. And what I mean by that is, if you look at this picture, if this car was self-driving, you would again have robots building robots. And robots like these have actually been successful in heavy manufacturing for decades, right? This is probably the most successful application of robotics. So, but you and I don't really see that in our day-to-day life, right? And so why is it that these robots are successful here and not elsewhere? Why is the future concentrated in this particular job in the factory and not in my day-to-day life? And I think there's a couple of things going on here. One is these robots are completely separate from humans, right? And in fact, you see here all over there are signs like, hey, keep away people, right? These robots are dangerous, they will crush you, right? These robots are great at doing very repetitive tasks in highly constrained, stable environments, right? If you had a human walking through this line somewhere, either that human would be very seriously injured, or they would completely shut down this production. These robots are just not capable of dealing with it. And they also aren't capable of adapting to a new task, right? If you introduce a new model of car, you have to reprogram this robot, teach it what exactly you want it to do on the new car. And so the next challenge for robotics and what we're trying to do with the new generation of robots is to overcome that. And so here are what I think are 4 examples of trying to do that. On the top left is Baxter from Rethink Robotics. This company, this is actually, I think now over 10 years ago, this company was trying to make a robot that was significantly cheaper than other alternatives. It was designed to be used immediately next to people. And you see that in all 4 of these images, right? These are environments where people are just walking about wherever they want, and there's no protective barriers around the robot. And what that means is that these robots have to be really good at sensing their environment to detect people and other obstacles, and then acting appropriately and safely in those environments. Another really great innovation, I think, that Baxter had was the eyes, right? You guys hopefully can see that this robot has a face, right? And the eyes would tell you where the robot is paying attention to. If you walk up to it, the robot might look at you and kind of raise its eyebrows like, yes, what can I do for you, human? Finally, I think one other thing that's unique about Baxter is the way that you quote unquote program Baxter, right? Unlike those robots in the factory that we saw earlier, the way that you might interact with a robot like Baxter is rather than programming, hey, this is what the widget looks like, and then this is what the box looks like, and then you have to make the move here, and then this is how you compute the trajectory, and so on. What you would say is you would walk up to it and say, hey, Baxter, you see these widgets on this conveyor belt? What I want you to do is pick them up and then place them in an empty compartment in this box here. And that's it. And then you walk away, and if everything goes well, Baxter does exactly that, right? So it's a new way of thinking and a new way of programming robots. Getting these robots to do exactly what you want them to do and making that process easy so that even somebody without a software engineering background can do it is, I think, one of the big challenges that's ahead of us, and something that many companies are working on. On the top right is a delivery robot. Being in San Francisco, I'm sure you guys have seen these, and they, as you can see, they borrowed the idea of having the robot having eyes from Baxter, so that robot also has eyes. Bottom left is Widget from Agility Robotics. Again, operates in an environment that's designed for humans. The whole idea, I think, with humanoid robots is that they be efficient and capable of operating in environments that are designed for people. So we don't want us to have to adapt to the robots. We want the robots to adapt to us, right? To work environments that are great for us. And then on the bottom right is an everyday robot from X, the moonshot factory, and again has to sense its environments and do simple tasks like wiping a table, which seems incredibly simple to us, but actually is from a robotic standpoint, I think, more challenging than say assembling that car that we were looking at earlier. Okay, so taking a step maybe a little bit even further back, let's look at the evolution of how we have been programming machines over time. What you see here are punch cards, and this fat stack of them on the bottom left is a single program, and you can see there are kind of marks in the middle of it, and each kind of separate stack of those cards, separate section of that stack, is a single function. And so these guys in the picture are sitting there punching holes into big cards. And so what they're doing is they're speaking in the language of the robot, right? Our computers currently run on binary, either 0 or 1. And so these humans are translating thoughts in their head into the robot's language, into binary, and then punching that binary into cards, and the robot then executes them. So this is how we started. Then we moved from that into assembly language programming, right? Now you're no longer dealing with binary, you're dealing with instructions that at the very least you can kind of read and pronounce. But there's a one-to-one correspondence between those instructions in assembly and to the binary that the robot uses, right? So we took a modest step in the direction towards human language, but we're still, I would argue, much closer to the binary language of the computer. And then we took another step up with compiled or interpreted languages, right? This is Python. I'm sure you guys have seen Python before and used Python. And actually, even just reading these instructions, I can kind of tell what that program is doing, right? It looks like there's a model and it's being compiled, and then that model is being fit to some data, right? And so that's another big step towards the language of humans, right? And if I were to ballpark it, I might say that Python is halfway between the language of humans and the language of computers, right? It's getting easier and easier, and that allows us to get things done faster and faster and makes computer programming more and more accessible to more and more people, and that's great. And now with AI, we're actually, I think, approaching the era where we go all the way to the language of humans and make the robots do the hard work of figuring out how to translate from human language into binary, right? A new way to program these robots might be, instead of you writing code, it might be saying, hey, drive around the office, and when you see some spilled liquid, clean it up, right? And you wouldn't necessarily think of the person who's saying that as a programmer, but I think in a fairly real sense, maybe they are, right? And if it sounds, you can probably kind of see the pieces of that already fitting from your everyday life, right? Your phone understands what you say to it. ChatGPT can kind of interpret that and respond back to you. Here's an example again from everyday robots of how they put that together. So this guy spilled something on the table and asked the robot, hey, can you help me clean up this mess? And the robot has to understand, okay, well, I clean up things with like paper towels and sponges. Oh, and where do I find a sponge? Oh, usually in the kitchen. Okay, so it goes in the kitchen. Where in the kitchen is it? Oh, it's probably in one of these drawers. Okay, so it looks through the drawers, finds the sponge, and brings it to the guy. There's a lot of things in the middle here that the robot has to figure out to be able to do that. And in this demo, he does just that, right? And I think that's super exciting and super incredible. So I hope that you guys come out of this talk as excited about the future as I am. And it's a great time to get into robotics, I think. Okay, so we're getting to the end of the talk. Some takeaways. One, the robots are coming near you. They're going to leave the factories where they've been kept isolated and far away from you, and they're coming to the streets and to your homes and to the shops and everywhere you go. The robots are coming. Neural networks and AI are taking over more and more of the software stack, right? Remember those diagrams we looked at, software 1.0 versus 2.0? We used to write all these things by hand as humans, and now we're just shifting that software engineering process to the process of gathering a whole bunch of data, saying what is success versus failure, and having the AI figure out the best way to distinguish between them. Because of those two things, specialized computing hardware for AI is becoming more and more important, right? AI is going to be all over us, and so you need to crunch a lot of data, you need to crunch it really fast, you need better computational hardware. And finally, AI kind of looks like a new computing paradigm, right? We're no longer translating our thoughts into the language of the robots, but we're making the robots and AI do the hard work of translating our language into hopefully what we want them to do and into them taking the appropriate action. And that is all I have. Thanks very much for your time, and I will be happy to answer questions.
Christoph, if I may add, amplifying what you just described here, number one, the development of artificial visual cortex will give, in the realm of AI, has been demonstrated to enable robots to watch and learn just like a baby, and some begin to call this cognitive robot, where they can watch and learn. Number one. On the hardware side, MIT's C-Cell just recently demonstrated the liquid neural network, which enable edge, low energy consumption drone to follow a walking target. And I think folks recently wrote about it because it's such a energy efficient AI implementation for today's AI. Just amplifying what you just mentioned, Christoph. And for the class, the last lecture of this 6 weeks is by Dr. Heiko Hoffman, previously with Max Planck, Planck Institute, talking about self-learning cognitive robots, culminating all these great talks by great speakers by Christoph and other industry leaders. All right, so don't miss the opportunity to converse with industry leader Christoph. The floor is yours, students. All right, so don't be intimidated. I'm going to. Did somebody wanted to ask Naomi?
Yeah, I had a question. Like what sets an AI specific part? Sorry. What sets an AI specific part, like apart from a GPU or like a gaming system?
So actually, in general, they are very, very similar. It's that whole parallelization of being able to do the same kind of calculation in parallel over and over. And so you can, and in fact, many companies still do. You can just buy a normal computer, stick in a gaming GPU, and it will be able to accelerate your robotics workflows really well. So I'm not sure that there's any particular differences there.
Thank you.
Will someone raise your Justin?
So a question I have is like speaking from like a GPU standpoint and like comparing like Nvidia to other companies such as like AMD, what is your like opinion on those said like competitive companies?
Oh, obviously I'm biased here. I don't know, and to be honest, my focus is more on software. So I would probably encourage you to do your own research from neutral third parties. I will say, one thing that I mentioned earlier was that Nvidia doesn't necessarily like to just compete on price. And so Nvidia looks for ways in which they can have creative, unique value adds in each area. And so, how can they tie in other things that their competitors won't necessarily be able to? So, for example, in cloud computing, right? Yes, they make the best chips, make the best kind of big AI chips, but they also make really good interfaces between those chips, so that now you can stack more of those chips and they communicate together really well. Oh, and also they connected to, now they're designing their own CPU, right? You guys may have heard about the new Grace Hopper super chip. So Nvidia is designing a system on a chip that has their own CPU and their own GPU and memory addressable by both of them, which means now you no longer have to copy data from CPU to GPU, and they also have like some of the best networking between those different cores. And so the thing that Nvidia looks for is, where can they be really unique in some particular way and not compete just on performance per dollar.
And if I may amplify what Christoph just said, and it's also a lesson for us, for you as future mover and shakers leaders, is that in addition to the ability to actualize your vision, you also need to strategically decide what the market needs and then make the pivoting. For example, Nvidia, Mr. Huang decided to exit the handset market altogether and bet everything on CUDA. That is what a leader should do, that you can see the market and you make a major decision. So this is, again, something that our future leaders want to learn. And as Christoph just mentioned, is Nvidia always focus on where it can add most value to solving the most urgent needs. Olivia.
Thanks for your talk today. I was wondering, what's your favorite project that you've worked on and why?
Good question. You know, I think every project has their own unique things that are super fun about it, you know, and I can probably find something really fun about every single one of them. You know, the work that I did at NASA JPL was the first my first job, and it was super fun. It was at the time, you know, humanoid robots were just starting. It was DARPA program, so that was just super incredibly exciting to be right on the cutting edge of computer vision and robotics. And then after that, at Kimi, one of the really great things about that was that it was a tiny team. There was, I think, 5 of us when I joined the company, and so because the team is so small and you have to build a whole business, right? It's not just a grad school project or a classroom project. You have to solve all these kinds of different problems that you never anticipated and that aren't in the area of your education. So you learn a ton, and it kind of allows you to have a diversity of the stuff that you worked on. So that was incredibly fun. Then at EcoGate, what was incredible was that I got to transition to actually leading the whole business, right? And so having to think really, really hard about the business side of things and being in an industrial setting where you have to talk to these you know, gigantic companies with many layers of employees. And so that's got me to flex a whole different muscle. In the job after that at Wavemaker Labs, what was fun about that was there was a whole portfolio of robotics companies, and so we got to learn about a whole bunch of different industries. So that was really good. And now at Nvidia, you know, Nvidia is just like among the greatest tech companies in the world, and so to be here is super exciting, and the work that I see being done here is just really great and cutting edge. And so the answer, I guess, is that every project has something that's been incredibly fun about it, and I think wherever you are, you can find hopefully something that you will truly enjoy.
And may I amplify also Christoph's comment? In San Francisco, lots of students are interested in becoming a software programmer. Unfortunately, the reality is that throughout our lives, statistically, we'll change our job. I think right now the latest statistic is about more than 10. So you are, on one hand, you are not stick with one job to be a coder in the DevOps program. That's extremely limiting. From Christoph's presentation, in terms of AI robotics area, it's huge. So many fields, hardware, software, AI. This is one aspect. So you want to expand your horizon, see the flow of one job to the next, where the industry is heading, and don't stick with the mindset being a coder in a DevOps program, number one. And number two, McKinsey just published a report that with generative AI, generating code, reusing the code, the jobs for coders will be reduced by the current estimate, 47%. So what the industry needs is exactly like what Christoph was just mentioned. The new paradigm of software could be is going to be AI based. There's so many coders who have generated so many similar Python codes for similar functions, right? So on GitHub, you can use GitHub. I mean, I'm sorry, Copilot to look for similar the deposit of so many codes. Therefore, we want to be like what Christoph said, go broad, look at all kinds of technology, exploring these various jobs that will fit the area that you are most comfortable with. Christoph, am I?
Yeah. Yeah, I think in some senses, yes. To me, it's not clear that actually the software engineering jobs are going to go away. I think tools like Copilot are certainly going to make software engineers more productive. And so in some sense, if you keep the number of software applications being written constant, yes, there would be fewer software engineers. But on the other hand, it's also possible that actually the supply of software engineers right now doesn't meet the actual demand. And if it might turn out that actually people want, and we have value for a whole bunch more software than we're currently creating. And so to me personally, it's not clear that the number of software engineering jobs are going to go away. I would say also, sorry, did you go ahead, Albert?
Oh, yes, you are absolutely right. And Christoph, we have conversations on this, and what the report says is also that the jobs, the required job in the market is senior software engineer who have an overall view. And indeed, as Christoph commented, these days the actually software programming capability itself becoming another basic skills for any STEM related jobs. So it's not that we don't need as many, is becoming the essential skills for every STEM related job. I hope I'm amplifying what you said here, Christoph. Okay, in the interest of time, Noah.
Yeah, thank you for your presentation today. It was really interesting. I see you have like like you've been all over like a lot of experience and like all the sides of it. Like with that, like where do you like really see like a lot of the improvements, like I guess the challenges like upcoming, like for robotics, I guess, like maybe like making it more mobile, or I guess compute power, or maybe from the software side, like what challenges do you see like the biggest challenges for AI and robotics?
Yes. Yeah, I think I touched on that a little bit. I think it's the transition from these highly structured and rigid environments like the factories, and towards dynamic, unstructured environments like the sidewalk where you and I walk, right? Where the robot has to operate in all these changing conditions. There's challenges all over the place there, right? From writing perception software, or helping the robot, I guess, write better perception software, to controls, to making better batteries, to making better sensors. One thing that we kind of looked at very quickly in that last video from Google, how that robot picks up that sponge, that actually like fine control, like picking up really small objects, that's a huge challenge. And there's a number of people that are looking into like how to get tactile feedback from the fingers, some are looking at making the robot soft too, right? So now when we think about robots, they're all covered in metal, right? So if the robot hits you, it's bad, and the robot has no sense that it's even doing that. Well, if you could make the robot soft, A, it wouldn't hurt you so much if the robot hit you, and B, you could also have some kind of sensor that detects that touch. And one way that people are doing it, which I think is just incredibly cool, is you actually have this like thick rubber membrane on the outside, and then that has a texture on the inside, and a camera pointing at that texture on the inside. And so when that membrane distorts, using that camera, you can see how it's being distorted, and so it gives the robot a sense of touch. There's also huge challenges in like how we as a society adapt to robots. And you guys probably are aware of that. In San Francisco, you have these people now putting cones on self-driving cars and stopping them, right? Like the robotics, especially now that you're leaving factories, it's not going to exist in a vacuum. It's going to interact with us. And so there's a whole bunch of challenges that aren't even just like engineering challenges, right? Similarly with self-driving cars, I don't think we've quite figured out what happens if your self-driving car hits someone, right? Who's liable? Are you liable, or is the car company who made the car liable? There's a lot of work to be done, and challenges all over the place. And maybe just piggybacking a little bit on what Albert was saying a little bit earlier, when you guys are figuring out what to work on, I would encourage you guys to be flexible and iterate and adapt, rather than having in your mind, yes, in 10 years I'm going to be working at X company doing X thing. I think the most important thing is to chase what the combination of what you're curious about, because if you're curious about something, it's not going to feel like work, and you're going to be much happier, and you're going to be happy to go way deeper than anybody else, right? If you're curious about something, you're going to go way down that rabbit hole where other people will stop and go grab dinner, right? And B, the intersection of that, and B, what you're good at, right? If you find that thing, chase it as deep as you will go.
Awesome,
Yes.
thank you.
Wonderful, wonderful conversation. I wish we have more time. We can easily go twice the time, and thanks what Christoph just mentioned. It's also a good time to mention that as Christoph and Aaron have yesterday both have mentioned, the legal aspect, the ethical aspect of AI robotics are so important. This Friday we have a guest speaker, Professor Reed Blackman, talking about ethical aspect, and 2 weeks ago we have also Professor David Capsule, who's a lawyer, a professor, a PhD, a professor. So this area, as Christoph mentioned, there's so many areas that we can work on in AI robotics. So I think the future leaders here, we really have so many things, so many opportunity ahead of us, and following Christoph's advice, be open-minded on all the possibility. Thank you, Christoph, for such an informative, such inspiring talk. We just cannot thank you enough. Just come back next year.
Yeah, I'll be happy to. Yeah, it was a lot of fun. Thanks very much, everybody. Hope you guys have a great rest of the program. Bye.
Thank you.
Yeah.
Thank you.
Thank you.